In this second revision model, we're going to cover a key concept about probability and ensembles. So why would we use probability theory? There's a famous quote from one of the pioneers of probability theory, Pierre-Simon de Laplace. So he says, La théorie des probabilités n'est au fond que le bon sens réduit au calcul. What it means, probability theory is at the end only common sense. It allow appreciating what the mind can intuitively perceive. Okay, and this is really the interpretation we're going to use throughout our application of reliability. So why would we want to use probability theory? Is it for describing random phenomena? Okay, at the end we need to ask the question, what is really random? For instance, if we have a coin, such as this one, and we flip it, whether it's going to land on head or tail, is it really random? So what does it mean to be random? So at the end, it's not really fully random in terms that it's not fully unpredictable. If I would exactly know, for instance, the initial position of my coin, the initial velocity, the initial angular velocity, I can reproduce the coin toss and get repeatable result. And for that, there exists some devices to do this. So if we say that if we can really control the if we can control the throw of the coin, we're going to get repeatable result. So it's not that a coin toss is inherently random. It's that we don't fully control the initial condition and we don't know them. And the system is kind of chaotic, meaning that the small perturbation in the initial condition will lead to a wide variability out in the outcome. So the system is not inherently unpredictable and random. It's just that we don't know the initial condition, and change in initial condition lead to wide variability in the outcome. So when we talk about something that is random, it's not necessarily unpredictable. So in our case, we want to use probability theory to represent not something that is unpredictable or something that varies, but more something that is unperfectly known. Okay, so we want to use what we're going to call epistemic uncertainty to represent lack of knowledge about some quantities, lack of knowledge about the properties of the material, lack of knowledge about what is going to be the exact loading applied on our structure. So take, for instance, here a large dam. So we wanted to characterize what is the Young's models at a specific point in that dam. That dam is already built. The Young's model is the stiffness of the concrete at one location. If we look at the time t, it's not varying. It's always the same value. It's just that I don't have a precise knowledge of what this exact value is, because the Young's modulus itself doesn't vary if we look at a time t. It's constant. It's just our knowledge of it that is imperfect. So what we want to do is to use probability theory to describe our state of knowledge of what that value could be. And one thing to keep in mind is that the less we know about a quantity, the more it becomes useful to use probability theory. If you have lots of knowledge, such as considering a deterministic value is indistinguishable from using probability theory, I mean, the added value for probability theory is really negligible. On the other hand, if you're working with quantities where there's lots of uncertainty involved into it, and you have even a hard time defining how to describe your phenomena probabilistically, then it's a point where it's essential to consider probability theory, because your knowledge is so uncertain that using a deterministic case there might lead you to completely wrong solutions. So who else is using probability theory? Actually, if you want to send a rocket in space, if you want to do robotics, the self-driving cars, the large language models such as ChatGPT, your Google search, all of these applications rely on probability theory. So one thing I can tell you is that if it works for them, it's going to work for us as well. So to look at an overview of what we're going to look in this module, we're going to first do a review of what is an ensemble. Then we're going to define probabilities. We're going to look at random variables. So we're going to look at univariate random variable. We're going to look at right, multivariate random variable. We're going to look at the notion of expectations. We're going to look at function of random variable, very important for a concept of reliability. And then we're going to look at what if these functions are linear? What if these functions are non-linear? And that still brings us at the first revision module here, but now about probability theory. Ensembles. So we're going to look at definitions, example of ensembles, and what are the elementary rules that apply on ensembles. So in terms of definition, we're going to say an ensemble is a group of element or events. So we say we're going to have our sampling space denoted by S as the ensemble of results that are possible. So everything that could happen. And this sampling space could either be continuous or discrete, finite or infinite. So in this case, if we're continuous, we're by default infinite because on a continuous range there are infinitely many possible values. If we're discrete, we can either be finite or infinite. So we're going to say we have an elementary event, so lowercase x. This is one possible realization in our sampling space S. Then we can have an event. So an event is going to be a collection of elementary events. And we can write something like this. So an event E belongs to the sampling space. It's going to be a subset of the sampling space. We're going to say our event E is a certain event if E equals the sampling space. We're going to say that E is an impossible event if it equals the null ensemble. This is going to be something that is impossible. E with a bar on top of it, we're going to denote this as the complement of E, meaning everything that belongs to the sampling space, but that is not E. And we can represent all of these things on what we call a Venn diagram. So the whole box is my sampling space. So S, this is the whole box. So my elementary event is my little point X. I can have E. E is going to be a collection of elementary events. And E bar is everything that is in S, the complement of E, everything that is in S that is not in E. Let's look at an applied example. So we have the state of a structure after an earthquake. So the reality is going to be a continuum from a pristine building to a completely collapsed one. But we're going to make, so this is going to be here our sampling space, a continuous one. We're going to make an abstraction and make it simpler. So we're going to say we're going to discretize this space and say my sampling space is going to be going from no damage at all to completely collapse. And in between, I'm going to have light damages or important damages. So I can shorten these notation to do no damage, collapse, light damage, important damage. I'm going to have 4 possible state in my sampling space. I can say I have a first event that's going to regroup both the no damage and light damage events. I can have my second one that is going to be just the collapse state EF. And I can say what is going to be the complement of E1. So whatever is in S, that is not in E1. So that's going to leave me with ID and EF. If I want the complement of E2, that's going to be everything that is in S, not EF, AD, LD, ID. So this is how it works. Second example, and is more tailored to the reliability problem we're going to face. So imagine we have the failure of this bar subject to a tight solid force. So S is the force applied on my bar, R is its strength, its resistance. So S solicitation, so this is going to be defined in R plus. The resistance R is also defined in R plus. So I can have my sampling space, which is defined in a positive two-dimensional real space. And I can represent this sampling space on such a 2D graph, where the horizontal axis is the resistance, vertical axis is solicitation. And in my sampling space, I can define a special domain. So for instance, everything that is above that purple line is my failure domain. Everything that is below is my survival domain. And my frontier here are all the tuple, the pair of value, such that the resistance equal the solicitation. Everything above here, the solicitation is above the resistance. Anything below resistance is above solicitation. So I'm going to have the failure of my component if R is lesser or equal to my solicitation. I can equivalently rewrite that equality as the difference between the resistance and solicitation lesser or equal to 0, just by sending S on the other side of that inequality. Okay, so now let's look at operations on events. So given the events E1 up to En, that belongs to the sampling space S. We want to look at the first operation, which is going to be the union. You can see union as OR. So we can say that we want E1 union E2 to be either E1 is there, or E2, or both. So if we represent it on a Venn diagram, I have my event E1, I have my event E2, and the union of E1 and E2 is either it belongs to E1, or belongs to E2, or belongs to both E1 and E2 together. The second main operation is going to be intersection. Intersection could be seen as AND. So if I have E1 intersect E2, so if we have nothing, it implies the intersection. So in this case, we want both E1 and E2 to occur simultaneously. We can generalize this to many cases. So we can see in this case, we have E1, E2, E3. This is the intersection between E1, E3. This is E3, E2, and E1, E2. And this is the intersection of 3 by 3, 3 terms. So E1, E2, and E3 occurring simultaneously. So the rules for the ensemble is that we can say that if we have E1 union E2, I can permute. So there's the commutativity there. So same thing for the intersection. We have associativity. So we say that if I have E1 union E2 union E3, where I have my parentheses here, the order that I will prioritize my operation doesn't matter. I can do the union over each term permuted anyway. So that allowed me to write in general way the union over each EI term for I from 1 to n as this union where I can permute the sequence in any way I want. So basically the union of all these terms is all the common space that is shared between all three. Then the intersection for a sequence of n term equivalently is going to be the intersection where all the terms happen simultaneously. For distributivity, I can say that if I have the parentheses here and I have the union of E2 and E3 that precedes E1, I can distribute my intersection operation into my parentheses to say it's going to be equal to E1, E2, union E2, E3. You can verify that this holds with this little exercise. And by convention, the intersection as priority over union. If it's not what you want to do, you need to use parentheses, because without any parentheses, we're going to always assume that intersection as priority over union. So let's look at some specific types of elements. So we're going to say that a collection of elements is mutually exclusive if any intersection between EI and EJ for any I not equal to J is going to be the empty set. So what it means is that there's not going to be any intersection between pair of events. So we can say, for instance, in this case, E1 and E2 are mutually exclusive. No intersection possible. If E1 occurs, events E2 cannot. We can have collectively exhaustive event, meaning that my collection of n events are collectively exhaustive if the union of all these events leads to the sampling space. So we can see here in the representation from E1 to En, if I do the union of all these events, I'm going to get the sampling space. And then we can combine both. We can say that events are mutually exclusive and collectively exhaustive if both their union lead to the sampling space and the intersection there are no intersection between any pair of events. So the difference between this and this, here we can allow for some intersection, here there are no intersection at all. And we can say that an event and its complement are always also mutually exclusive and collectively exhaustive. One key rule which we're going to use when, I think in module 9, where we're going to deal about system reliability, is the Morgan rule. So it says that we can represent the intersection of the complement of event as the complement of the union of the event. Okay, that might seem tricky, and we have the kind of complement to this, which is the union of the complement of event EI is equal or can be represented by the complement of the intersection of event. So if we put that into practice in a context of reliability, imagine that to be able to reach a departure from an arrival point, we need to cross n bridges. Okay, and we say that it might be a little twisted, but the event EI represents the situation where a bridge, one of these bridges, is not open to the traffic. So we're going to say that our system is going to be failing if we have the union of our nth event. So basically, we're going to fail if E1 is not open to traffic, or E2 or E3 or En or any of those combinations. So we can represent the failure here as the union of our event EI, bridges not being open for traffic. We can then represent the complement of the failure, which is survival, using the De Morgan rule. So we can say that the complement of this, we know that the complement of failure is survival. So I have just the complement of this, and that should give me the survival. And from the Morgan rule, we see that we can represent this as also the intersection or a complement of EI. So the complement of EI, meaning the bridge is open to traffic. So it means that to cross from a departure to an arrival point, the bridge 1 must be open, and bridge 2, and bridge 3, and bridge 4. Okay, so we see that it holds here. So we've seen what we needed for ensemble. Now let's dive into probability. So we're going to look at introduction, what are the axioms and elementary rules for probability, and then we're going to look at conditional probability and Bayes' theorem. So first, if we look at the interpretation we're going to do of probability. So when we look at the probability of an event EI, we can have the Bayesian interpretation. So probability of EI measure the likelihood of the event EI with respect to all possible events in my sampling space S. So it depends on our prior knowledge of EI, and that means my knowledge of the probability EI might change in time as I collect new information. So this is what we call the Bayesian interpretation. The opposite is the frequentist interpretation. So in that case, I'm going to interpret the probability of an event EI as a limit as an event tends to infinity, as the frequency of an event divided by the number of trial I've done. Okay, and whatever happened with the probability theory and the advanced application in either machine learning, robotics, and all of this are more relying on this Bayesian interpretation, that this frequentist interpretation. And this is what we're going to use in the context of reliability theory. If we look more at the fundamental axioms, okay, so the probability of an event must always strictly be between 0 and 1, where the two extreme case, if it's 0, it's the probability of the null space. If we have 1, it's the probability, it's 1 is the, we're sure to land in our sampling space. So probability of the sampling space is 1, it's a certain event, and the probability of the null event is 0. So if we have two events that are mutually exclusive, we can say that the probability of the union for E1 union E2 is going to be the sum of the probability. Because if they are mutually exclusive, they cannot happen together. So the probability for the union of both is simply going to be the probability of the sum of the probability for each event taken separately. So we can define the probability of a complement of an event. So E is an event, E bar is its complement, as simply 1 minus the probability of the event. So from this, we can see that the probability of the null ensemble is 0, because it's 1 minus the probability of the sampling space, which is by definition 1. So in the general way, we can define the addition rule for the probability of the union of E1 and E2, two events. So before we were making the constraint that it has to be mutually exclusive. But if we want to look at a general case where they're not necessarily mutually exclusive, they can happen E1 and E2 simultaneously. We need to have probability of E1 plus probability of E2 minus the probability of E1 and E2 occurring simultaneously. Where does this come from? If we look at the Venn diagram here, now E1 and E2 are not mutually exclusive anymore. They can simultaneously happen in this intersection here. If I sum the probability of E1 and E2, I'm going to double count the probability that is located at the intersection here. So that's why I need to remove the probability that is for the intersection in order to avoid double counting it. And we can generalize this concept in what we call the inclusion-exclusion rule. So if we want to define the probability over union of a collection of an event, in that case, what I'm going to do, the first thing I'm going to do is I'm going to sum the probability for each event taken individually. Then I'll have to remove the probability for each intersection between pair of event. And here we have to be careful. We have I lower than j for the indexes, meaning that we don't want to double count the permutation. Okay, it's for any pair ei, ej. We don't want to switch for ej, ei to double count them. Then if I do this, I'm going to have a lower bound on the probability. I need to add all the intersection between triplet, then remove all the intersection between quadruplets, and etc. until I have my n term. And using the De Morgan rule, I can represent this equivalently as 1 minus the probability for the complement of the intersection of all the complements. So if we look at this inclusion-exclusion rule for a simpler three terms operation, so we want to express the probability for the union between E1, E2, and E3. I'm going to start by summing the probability of each event individually. Then sum for the probability of intersection for all the three possible pairs, plus the probability for the intersection of the three terms together. And we can see then when we do this, if we have event E1 here, E2, and E3, the events there are counted once. These are the three terms here. Here, they would be double terms. So that's why we remove them. And if we remove these three terms, we will have removed the intersection there. So that's why we need to add it at last. And this inclusion-exclusion rules looks like this. So initially when we're going to sum, we're going to have an upper bound on the true probability for the union. Then we remove the second pair of terms, we're going to have a lower bound, upper bound, lower bound. And we're going to oscillate like this, and we're going to converge asymptotically to the true value for the probability of the union. An issue with this is that when we have the union of a large number of terms, we have a large number of terms to evaluate, and evaluating the joint probability for lots of events can becomes increasingly difficult as n increase. But here, the silver lining in the story is that the contribution of that higher term reduces as we increase the number of terms. So if you look at what is the probability of being struck by lightning while being eaten by a shark. Okay, we take two unlikely event, we look at the intersection, the probability that both happen at the same time is vanishingly small. Okay, and the more events you're going to include like this, the lower the probability is going to be. We're going to reuse this concept when we're going to look at the reliability of system in Module 9. Now we're going to look at conditional probability. How can observing one event give us additional knowledge for another event? So this is going to be seen through conditional probability. So we're going to say that probability of E1 bar E2. Okay, this is the condition. So whatever is on the left is the thing for which the probability is characterized, and whatever is on the right is what you observe. So what is my probability of E1? We can read this as given I have observed E2. So by definition, a conditional probability is defined as the division between the joint probability for the intersection of E1 and E2 divided by the probability of E2, assuming that the probability of E2 is not equal to 0. So we can write this down if I send my E2 terms on the left-hand side as the joint probability between E1 and E2 is the product of the conditional E1 given E2 times the probability of E2. When we're going to multiply like this, it's always what is going to be on the right-hand side that's going to multiply what is the marginal probability. When we say, so this is a conditional probability because we have that given here. This is a joint probability because we have the intersection. And we have here a marginal probability because we have a single term into it. But the thing is, to represent that joint probability, I have two ways of doing so. I can just say E1 given E2 times E2, or E2 given E1 times E1. Both are admissible way. And at the end, what does this represent is that, as we saw earlier, that intersection over these two events, what is the probability defined over that region? And we can say that two events are statistically independent, and we're going to represent that independence by the symbol. So it's a inverted T with two vertical bars, as you can see here. So we can say that two events are statistically independent if the conditional probability of E1 given E2 equals the probability of E1. So what does it mean? So whether or not I observe the value of E2, it doesn't change the probability or my knowledge of the event E1. So if I have this statistical independence, I can represent the product of the probability for the joint event E1 and E2 as the product of the probability for each of the event taken separately. So now we're going to look at the more extensive case for defining joint probability using the chain rule. So if I want to represent the probability for the intersection of n events, so in that case, what I can do is I can break that joint probability in conditional and marginal or joint probability. So in that case, I want to break it down. I think I'm going to have the conditional probability of E1 given E2 up to En. And then I can represent probability of E2 up to En as a single block. But then I can carry on, break it down. I'm going to break it down E2 here as well, given E3 up to En. Probability times E3 up to En. And I can carry on doing this until I'm going to have n terms, which are n minus 1 of them are conditional probability, and 1 is going to be a marginal probability, the last one. And here I can permute the order in which I do this breaking down of the operation. For instance, if I have the probability for the intersection of three events, E1, E2, E3, I can break it down into probability of E1 knowing E2 and E3, probability of E2 knowing E3, and probability of E3. And where if I take the product of these two, so probability of E2 and E3, if I multiply these three, I retrieve what I add on the left-hand side. So the law of total probability, I can see this as if I have an event A that belongs to my sampling space S, so A belongs to S, and if I have at the same time a collection of n events that are mutually exclusive, collectively exhaustive, that also belong to S, so in that case, I can say that the probability for my event A can be obtained by applying this rule. So I can sum over all index I from I equal 1 to n, my n mutually exclusive collectively exhaustive event. So it's going to be probability of A knowing EI times probability of EI. So we can represent this on a Venn diagram. I have my n mutually exclusive collectively exhaustive event, and I have A that can overlap some or all of these events. So I can define the probability over A as the intersection of A and EI. So this give the product here is going to give me the intersection or the probability over the intersection of A and EI plus A and E2, A and E3, etc. Okay, and this operation is akin to marginalization. So I'm going to have here joint probability, and I'm going to sum on the variable I want to remove. So in this case, my event is mutually exclusive, collectively exhaustive. So if we carry on our application of the total probability rule, so in that case, I can apply this in order to say that I can also apply this operation when I have the probability over the union of event or over the intersection of events. So if, for instance, I have probability of A given B, I can sum over all I from 1 to n for probability of A given EI times B, probability of EI given B. And the product of these two terms is going to be the joint between A and EI, and I sum over all the possible EI, just going to give me probability of A given B. Now let's look at Bayes' theorem. We're going to use this in module 11 in order to gain knowledge from empirical observations. So how can observing some phenomena give us knowledge about the random variable we're interested in. So given a collection of an event that are again mutually exclusive, collectively exhaustive, I can represent the joint probability between A and EI in this way, the same thing we saw in the previous slide. And we saw that we have two ways of representing this joint, either A given EI times EI or EI given A times A. So in this case, if I put these two terms equal to each other, I'm going to have these terms. And if I reorganize these terms, we're going to obtain what is called as Bayes' theorem. If I'm interested in characterizing what is the probability of my event EI, given that I've observed A, I can represent this, and this is going to be called a stereo probability, as the likelihood of observing A given EI, so the probability of A given EI, times the prior probability of the event EI, divided by a normalization constant, or also called evidence, the marginal probability of the event A. And this application of conditional probability will allow us to learn from events how does it modify our knowledge of other random variables. So if we look at this through the Venn diagram, we can represent the probability of an event EI, given that we've observed another event A that occurs. We can represent this as the probability of A given EI times EI, divided by the probability of A. And we can see here that for this representation, where we have four events E1 to E4, we have another event A. Given that I have observed that A occurred, what is the probability of, say, E1 given that A occurred? It's going to be the probability defined over the intersection of the two here, divided by the probability of anything that happens over A. So this is what we can see here in that division. This is what Bayes' theorem is doing. It's basically simply an application of probability theory. And here, what we have on the normalization is my normalization constant. And typically, when we have a large number of events, P of A might become very hard to compute. We're going to dig into deeper detail into this later on in the course. So let's look at a simple application of conditional probability and Bayes. So let's imagine we have the sampling space for the intensity of an earthquake being light, moderate, or important. Then we have a structure that is built in the region that can be in either two states. The state could be, the sampling space for the state could be either damaged or the complement not damaged. So we know these conditional probability, okay? So we know that the conditional probability of damage given a light earthquake is 1%. The conditional probability of damage given a moderate earthquake is 10%. And the probability of damage given important earthquake is going to be 60%. And knowing this, we search what is the marginal probability of having a damage. So in that case, we need additional knowledge, which is what is going to be the prior probability of each of those earthquake intensity. So we are going to say it's 90% for light, 8% for moderate, 2% for important. And note that the sum over all these three equals 1, okay? Because this is a probability. So the sum over all the sampling space must equal to 1. Then these are conditional probability. So they don't necessarily need to sum to 1, okay? Because they are conditional probability. If I sum over what is on the right-hand side, it doesn't have to sum to 1. It's only if I would be summing over all the possible probability here where it would need to. So in that case, if I want to have the marginal probability over my states, so whether there's, in this case, damage, I'm going to multiply these conditional probability times the marginal. I'm going to sum over all possible states. So that's going to be here damage given light earthquake times probability of light earthquake, damage time given moderate earthquake times probability of moderate earthquake, damage times important earthquake times probability of important earthquake. And if we fill in the numbers, we're going to get here 0.029 as the probability of having damage. Now, if we want to reverse this operation, let's imagine that we've observed damage on building. We want to infer what was the intensity of the earthquake. So we can use Bayes' rule to revert these operations. So we're going to say, what is the probability of an earthquake of important intensity given that I've observed damage? So I can use this through Bayes. So it's going to tell me I need to use the conditional probability of damage given the intensity that is important in this case, times the prior probability of important damage divided by the normalization constant that I just compute, the marginal probability of damage. So that 0.29 is what we computed just previously. We add 0.6, the probability of damage given an important earthquake times 2%, the probability of important damage. That gives me my posterior probability of important earthquake, given that I've observed damage on my building, which is now 41%. And keep in mind, my prior probability of important damage is initially 2%, but no, sorry, my prior probability of an intense earthquake was 2%. But if I observe damage, D, it move up my probability of important damage to 41%. I can do the same thing for moderate and for light damages, where we can see that these probability are lower. And especially for the light damage, my probability for light damage was initially 90%, but for a low intensity earthquake was 90%, but after I perceived damage, that probability dropped from 90% to 31%. Okay, so now we're going to look at random variable. These are really the tools we're going to use in the context of reliability theory. So we're going to look at an introduction. We're going to do two types of variable, either discrete or continuous. And we're going to look then at conditional probabilities. So we can see random variable as a representation of a sampling space on a line. So instead of having a sampling space that we had like this before, we're going to represent x as our random variable on a continuous line, where s here is going to be our sampling space, and a subset of our sampling space is going to be defined as an event. In terms of notation, the lowercase x represent a realization or one possible value that my random variable can take. And capital X is going to be my random variable. A random variable in itself doesn't take one specific value. It can take any value in the sampling space defined for x or lowercase x. So the probability that the random variable take a specific value lowercase x is going to be either described by a probability mass function in the case of discrete random variable, or a probability density function in the case of continuous random variable. Let's start with discrete. We're going to say we have a PMF, probability mass function, that describe the probability that any value of my random variable can take. So we're going to say lowercase p with the subscript of my random variable capital X, evaluated the value lowercase x, is actually defining what is the probability that my random variable x equal a specific value. So the property of that PMF is that it's going to be strictly defined between 0 and 1, and the sum over all possible value x must be equal to 1, so that the probability over the sampling space must always be equal to 1. So the ensemble of possible value x is must be mutually exclusive and collectively exhaustive. Okay, this is always true for any values on which we define a PMF. So let's look at the example of the damage in the structure. So our sampling space F is going to be either no damage, light damage, important damage, or collapse. So we can define here on our real space for these four possibilities, and the height of the bar is going to represent the probability of each of those events, and the sum of these probability must obligatorily be 1. We can create an event. So an event x between 1 and 2 is going to be the collection of probability of these two events. Then for the continuous case, so we're not going to use probability mass function anymore. We're going to use probability density function. Why? Because the probability that a random variable x equal a specific value is always 0. Okay, because there's infinitely many possibilities. So now if we want to define a probability in a strict sense that is not 0, we need to define this over a slice of width delta x. So the probability that x, my random variable, is between x and x plus delta x is my probability density times the infinitesimal slice delta x. So for instance, if we want to define this, delta x would be the width of a slice, and this would represent my probability density. So for my probability density, now we can see that the continuous integral over this curve, so basically the area under my probability density, must by definition be equal to 1. And now my probability density must be larger or equal to 0. And keep in mind, at the end, my probability density might be larger than 1 because at the end, it's not a probability, it's probability density. So what matters is that my integral underneath my domain equal 1, not the value itself of my probability density. So we can now have a cumulative density function. Cumulative density function are going to be represented by capital F. We're going to have the subscript, which refers to the random variable capital X. And we're going to have the value at which the CDF is evaluated lowercase x. And what does this represent? It represents the probability that my random variable x is lesser or equal than the value x I want to evaluate it at to. In the case of discrete random variable, we're going to sum over all possible value x prime lesser than x. In the case of random variable, we're going to look at the PMF we had earlier. If we want to draw the cumulative density function, a CDF, we're going to see that this is going to be the staircase we have here, where for the highest value, it's always 1. For the lower value, it's going to be 0. So if we want to do this in the continuous case, so in the discrete case, we were summing. In the continuous case, we're going to integrate. We're going to integrate from the lower bound minus infinity up to x prime, the value at which I want to evaluate my CDF. So this represents here the cumulative area under the curve up to a certain value x. And the special property we have is if we evaluate that CDF at the lower bound, say minus infinity, we're going to have 0. At the upper bound, we're always going to get 1. So we can go between PDFs, so probability density function, and cumulative density function by either integrating or differentiating. So for instance, we can obtain the CDF of x by integrating my PDF from minus infinity up to the value x I want to evaluate. On the inverse, I can obtain my PDF by differentiating my CDF with respect to x. For discrete random variables, I can obtain my PDF by simply looking or differentiating, taking the difference in my CDF value at 2 consecutive points. The common probability density that we're going to use in the context of reliability theory are going to be seen in the next module. But for now, for the sake of later on developing the context of expectation, we're going to take a little glimpse as the normal or Gaussian random variable. So we're going to say in terms of notation that x is distributed like a Gaussian or a normal random variable that is defined by 2 parameters, mu the mean and sigma the standard deviation, sigma square being the variance. So let's take it for granted for now, but let's assume this is the equation to define the PDF of a Gaussian random variable. So if we want to obtain the CDF, we're going to integrate that formulation I miss with respect to dx. And we can see here, we have the PDF for a mean equals to 1 and standard deviation going to 1. And we have the CDF, which is going to be the integral of this curve. We're going to come back to this later on in detail in module 1. So now if we look at the conditional probability for random variable, imagine that I have an event E and a random variable X. And I want to know what is the conditional probability of my event E, given that I've observed that my random variable is equal to a given value, lowercase x. So E1 given E2 is the division between the joint probability for event E1 and E2 divided by the marginal probability of what I have on my right-hand side, E2. So it means if I want to have the conditional probability of E2 given that my random variable x equals a specific value, lowercase x, it's equivalent to write this down as the probability for the intersection of the event E and the event where my random variable equals lowercase x, divided by the probability of what I have on my right-hand side, the marginal probability of x being equal to a specific value. I'm never going to write stuff with this amount of length. I'm going to say first, I'm going to remove these brackets to represent the event. I don't need them. Sorry. Then I'm going to say I can represent this intersection by a conditional probability and a marginal. So probability that x equals x given the event, and probability of the event is going to give me the join between event and my observation. And typically I'm not going to explicitly represent the random variable. I'm just going to say probability of event given x is probability of x given the event times probability of the event divided by the marginal probability of the event. But implicitly, it means the same thing as what I've written in the long form here. So now let's look at conditional probability for events. F, if x is a discrete random variable, so we can say that the probability of the event given x is the probability of E given x is the PMF of x given the event. So conditional PMF times the prior probability of the event divided by the probability of x. So the marginal probability of my event x. So we can revert this. So if we say, what is the probability of my random variable x taking a specific value? So what is my posterior probability mass function given that I have observed A? So here there was a probability. Here is going to be a PMF. So we can say that this is a updated PMF or posterior PMF for all my possible value x given that E occurs. It's going to be a probability of E given x times my marginal probability of x divided by the probability of my event. So now if we can do the same thing, if x is a continuous random variable, we're going to replace here the PMF lowercase p by f, which is going to be a probability density function. And we can revert our example. Here's the same thing. So far we've only looked at univariate random variable. Now we're going to extend what we've seen for multivariate random variable. We're going to look at joint probability density function and conditional joint probability. So we have a vector of random variable for x1 up to xn. So this is a vector. Keep in mind, whenever we represent a vector, we always assume it's going to be a column vector. So this is capital X. So this is my random vector, and X represents the possible realization of my random vector. So why would we use this? To describe the simultaneous occurrence of multiple phenomena. I want to describe a bridge. I want to describe what is going to be my joint knowledge between the property of, say, the concrete. So what's going to be the joint probability of a given value of Young's modulus and ultimate compressive strength. Okay, these two might be dependent upon each other. I want to represent them as a joint occurrence. So if we want to represent a joint probability mass function, I want to have P of x that is now bold. This is going to be the probability for x1 equals x1, intersection x2 equal x2, up to xn equal xn. So again, that joint PMF must be strictly between 0 and 1. And I can marginalize from my joint PDF. So for instance, if I sum over all possible value for my nth variable, I'm going to remove it from my joint probability. Okay, this is the operation that's called marginalization. I don't have to sum over the nth variable. I can sum over any ith variable, and it's going to remove it from my joint distribution. If I sum over all the variable on my joint PMF, I'm going to by definition obtain 1. And if I look at just the ith variable in my probability mass function, we're going to call this a marginal probability mass function because marginal refers to a single term. So we're going to look at this marginalization operation in application. Imagine that we have two discrete random variables that are both statistically independent. I can have my PMF for x1, probability of x1 equal to 1 is 0.1, x1 equal to 0.5, x1 equal to 3.4. If I sum these, I'm going to obtain 1. I can have similarly my marginal PMF for x2 given by these numbers, and I can obtain my joint PMF for the occurrence of x1 and x2 simultaneously by doing point by point the product of my marginal PMF for x1 and x2. So we can see the marginal for x1 represented in red here, the height of these stems. The marginal probability of x2 represented by the blue stems, and any height of the bar here represents the joint occurrence between x1 and x2 obtained by the product of, say, x2 equals 1.8 times x1 equal 1 equal 0.1. That's going to be the height of my bar here. So if we represent the height of these bars as a table, so each row represent x2, each column represent x1, and we have the joint probability for both occurring simultaneously. If I want to marginalize, say I want to marginalize the effect of x2, I'm going to sum over all possible value of x2. So I'm summing here over a column. I'm going to retrieve 0.1, 0.5, 0.4, which does represent my marginal probability mass function for x1. So this is what marginalization does. Now, if we do the same thing for continuous random variables, the representation of multivariate random vectors. So I can represent f of x times delta x by the probability that x1 is between x1 and x1 plus delta x1. I can do this for all and random variables. As a property, sorry, my joint PDF must strictly be greater or equal to 0. And keep in mind again, it can be greater than 1 because what matters is that the integral underneath my joint PDF equals 1. If I want to marginalize, I'm going to replace what I had as a summation for discrete random variable for now and integral. If I integrate over the nth variable, I'm going to remove it from my joint PDF. If I integrate over all my dimension, I'm going to by definition obtain 1. And if we look at just one dimension, it's going to be my marginal probability density. So again, we're just going to take a very brief overlook about a very common probability density, which is the normal one. In a bivariate domain, it looks like this. So this is the equation for the bivariate normal or Gaussian PDF. Right now, we're just going to take a glance at it. We're going to cover it in detail in module 1. What I want you to see here is that we have 5 parameters that define it, both the mean for each variable, the standard deviation for each variable, and rho, which is what we're going to see soon as a correlation coefficient. So these 5 parameters can be assembled in a multivariate domain as a mean vector, which concatenate the mean of each value, and a covariance matrix, where you see that the covariance matrix that define my multivariate random variable, the Gaussian random variable. In this covariance matrix, I have my standard deviation squares on the main diagonal, and on the off-diagonal term, we have the correlation coefficients times the pair of the standard deviations. And we can see that for values of this, so mean values are 0, standard deviation of x1 is 2, standard deviation of x2 is 1, and my correlation coefficient is 0.6. It gives me these marginal PDF for x2, for x1, and my joint PDF, either represented as a surface or a contour plot. We're going to come back to this example again in detail in module 1. So now we can look at, in the continuous case, the multivariate case, we have CDF, cumulative density function. So it represents what is the joint probability that x1 is lesser or equal to a certain value x1, x2 lesser or equal to x2, etc. So again, that joint CDF must be strictly between 0 and 1. And if we evaluate that joint CDF for any value at its lower bound, it's going to give me 0. Okay, I don't have to evaluate all of them simultaneously. Any of those dimension evaluate minus infinity is going to be 0. If I simultaneously evaluate all these dimensions at their upper bound, so plus infinity, is going to give me 1. Then if I evaluate my joint CDF for an arbitrary number of variable, and I evaluate one of those variable at plus infinity, this is going to be equivalent to marginalizing that variable. So removing them from that joint CDF. So I can do this for any variable, not only the nth one, for any of them. So I can obtain my joint CDF by the multivariate integration on my joint PDF. And equivalently, I can obtain my joint PDF by differentiating my joint CDF. So if we look at this again very quickly in the context of a Gaussian or a normal random variable, I can obtain my joint CDF by integrating my joint PDF. And it would look like this. I would have my marginal CDF for x1 in red, marginal CDF for x2 in red, and this is my joint CDF for x1 and x2 represented here as a contour. Okay, now let's look at last time conditional probability for, firstly, discrete random variable. If xi is a discrete random variable, so I can represent the joint probability for x1 and x2 like this as my conditional probability of x1 given x2 times marginal probability of x2. I can represent it the other way, x2 given x1 times probability of x1. So if I reorganize these terms, I can represent the conditional probability x2, x1 given x2 using base theorem like this. I can revert these terms. If instead of observing x2, I would observe x1. So in the case where I have the statistical independence between x1 and x2, I can say that the conditional probability of x1 given x2, as we've seen earlier, is simply the probability of x1. That means observing x2 won't change my knowledge about the probability of occurrence of x1. And in this case, where I have statistical independence for a set of n random variable, I can model that joint probability for n variable by simply taking the product of my marginal protein mass function. In the case where x1 and x2 or x1 up to xn are not statistically independent, we need to use the chain rule to define that joint probability between an event by n minus 1 conditional probability and 1 marginal PMF. So for instance, a bit as we saw earlier, the joint probability for the event x for the random variable x1, x2, and x3 is going to be x1 time given x2 and x3 times probability of x2 given x3 times probability of x3. So in the case where we have continuous random variable rather than discrete, it's the same. We're simply going to replace our little p by a little f, going from a probability mass function to a probability density function. Okay, so now let's move to the notion of expectation. We're going to see what is an expectation, how does it help us to define the moment of order m, how does it allow us to define a concept of what is a variance, where does it come from, what is a covariance, and how can we define the matrix notation for variance and covariances. So first, what is a mathematical expectation? So these are going to be the weighted sum of all possible value of a random variable. So in the case of a continuous random variable, the expectation of x, so that symbol E is denote the expectation. So the expectation of x is going to be the weighted sum of the possible realization, lowercase x, times their probability density of occurrence. We integrate over all possible value x. So in case we have discrete, we're going to simply replace that integral by a sum. So the expectation is a linear operation. So it means that I can rewrite this expectation over a function of random variable where the function is deterministic as the evaluation of my function at the deterministic value times the probability density of the possible value of a realization of x. I integrate over all possible dimensions. And that will allow me to define the moments, okay? And what is a moment? So if we define the moments of order m as the expectation over a random variable x to the power m. So in that case, that's going to say I'm going to have the integral over x for x power m, a possible realization, weighted by its probability density. So for m equal 1, the expectation is going to be equal to the mean. Okay, so or the expectation. And if we want to relate this to the concept of structures, when you have a cross section, say for a beam, this center of mass, center of gravity, represent the mean. Okay, the point at which you could balance that cross section on your finger. This is the same thing for probability density or probability mass function. The mean represents the point on that probability density or probability mass function where you could, if you put that probability density on your finger, you could balance it over. Okay, it's like kind of its center of gravity. For a moment of order 2, it's going to be expectation of x squared, expectation of the square. It's not really meaningful or interpretable. But it allows us to represent now the centered moment of order n, which are defined by extension, the expectation of x minus the mu x, so the mean, to the power m. So the center is because we correct by subtracting the mean. So in that case, by applying the same kind of analogy here, we're going to integrate x minus mu x. So here's a little typo. It should be lowercase x minus mu x. It's not a random variable. It's the realization that is going to be weighted by its probability density. So for m equal 1, we know that the expectation is 0. Not very interesting. But for n equal 2, what we retrieve is that the result is what we're going to see is the standard deviation square or the variance. And if we go again to the analogy for a cross section of a beam, the moment of order 1 is equivalent to the center of gravity of our cross section. The centered moment of order 2 is going to be what we're going to call the variance. And for a cross section of a beam, that would be the inertia. How much in a cross section the material is dispersed around the center of gravity is going to be the inertia. In the case of a probability density or probability mass function, how much that probability density function is spread around its expected value. So if we dig a little deeper in the notion of variance, what we just defined earlier, in short form, we're going to define it like this, sigma square. So the standard deviation square is going to be my variance. And I can rewrite this term by developing this here as the expected value of x squared minus the square of the expected value of x. This is a useful identity that is used when you multiply some analytical concept. So the variance of x, as I said earlier, will measure the dispersion of my probability mass or probability density function. It's going to be represented as sigma x squared, which is my standard deviation. Another measure we typically use is the coefficient of variation, COV, which represents the ratio between my standard deviation and my mean. And this is meant to be used for mean that are different from 0. Now let's look at the concept of covariances. How much two variables move together simultaneously. So given that I have two random variables xi and xj, I can represent the covariance xi xj as the expectation of xi minus mu I times xj minus mu j. And we can rewrite this in this, the expected value of xi times xj minus the product of the expectation for the marginal random variables. And here, that's going to help us define the correlation coefficient. So the correlation coefficient will define what is the amount of linear relationship I have between xi and xj. So for instance, let's take a little bit outdated example where we have the age of a husband and a wife in a couple, but we can see that empirical data show that there's that linear trend, meaning that it's not a fixed rule that whenever someone is 70, the other member of the couple is 70 as well. But it shows a linear tendency. And the stronger this linear tendency is, the higher is my correlation coefficient going to be. So strictly speaking, my correlation coefficient rho must be between -1 and 1. And it's defined as my covariance between these two random variables divided by the product of the standard deviation. And one property we have is that if two random variables are statistically independent, so xi is statistically independent of xj, that implies that my correlation coefficient rho ij must be equal to 0. Okay, so we can look at an example here. We have two random variable, x1 and x2. So that cloud of point is circular, indicate that I have no correlation. These variables are statistically independent. If I would have a positive, stronger correlation, you can see that all the points would align in the extreme case along a line. If I have instead of positive and negative correlation, they're going to align according to the other diagonal. So meaning that high values for one are going to be correlated with low value of the other one. The second line here represents the case where we don't have the same standard deviation for sigma I and sigma j. So in that case, the value of sigma I is much larger than sigma 1 is much larger than sigma j. So the other thing we can see here is that we said that if two random variables are statistically independent, their correlation coefficient is 0. But the inverse is not true. If we have no correlation coefficient, it doesn't mean that our variable are independent. Why? Because we can have non-linear dependency. So in the big picture, what does being dependent mean? It means that if I gain knowledge about one variable, does it change my knowledge of the other variable? Okay, in nonlinear case such as this one, what we see on the third row, all these cases would score 0 in terms of correlation. However, we can clearly see that there's some dependency. For instance, in this case, if I observe that my value for the horizontal axis is high, it tells me that my value for the vertical axis should be high as well. Okay, so we have dependency because gaining knowledge about one variable tells me about what should the other variable be. But these are not well captured by the correlation coefficient because they are not linear dependency. And finally, another thing to note is that it's not because variables are correlated that there's necessarily a causal relation between them. And the classic example for this is cold weather and flu. So we can typically see that whenever temperature gets cold, the number of flu cases increases. So we can think, oh, but the cold is going to cause the flu. Not really, okay? Take an isolated person, bring them up north in cold weather, and that person is alone in the wood. That person is alone is never going to catch a cold because it's not the cold itself that cause the disease or the flu. It's really the viruses that is shared by person to person. And why we see increase in case of flu and when it's get colder is because everyone gathers indoor with closed windows and there are more interaction in closed space that favors the transmission of viruses. So it's not the cold itself that caused the flu, it's just a co-founding factor. Now, if we generalize these initial expectation in a matrix notation, so if we have an n-dimensional random vector x, we can define its mean vector as the concatenation in the vector of all its mean, and we can define a standard deviation matrix where we're going to have dxx as being a square matrix where all the terms are going to be 0 except the terms on the main diagonal, which are going to be its standard deviation. So whenever you see sim like this is because it's symmetric above and below the main diagonal. We're going to have Rxx, which is going to be defining our correlation matrix. By definition, a correlation matrix is again a symmetric matrix where on the main diagonal we have 1, and for the upper and lower triangular part of the matrix, upper and lower diagonal, we're going to have the correlation coefficient for any pairs of random variables. And finally, we can have our covariance matrix, which can be obtained by decomposing or multiplying DRD. That's going to give us our full correlation matrix. And by definition, a correlation matrix is always going to be the same thing. On the main diagonal, I'm going to have my vector of variances for all my variable, and any of diagonal term is always going to be a rho ij times sigma I times sigma j. Okay, so now key aspect for reliability theory, function of random vectors. Okay, we're going to look at definition and what are the transformation rule that we need to use here. So let's assume that we have a deterministic function g of a random vector x. So this is going to be an n-dimensional random vector defined by a joint PDF f of x. So given that we have here y, which is the output of g of x, which could be m-dimensional, where x is n-dimensional, this is going to be equivalent to outputting m function that's going to be univariate output that all takes as input an n-dimensional random vector. So the question is, how can we define the joint probability for the output y, knowing the joint probability for the input x? So we're going to look at three specific cases of interest. The first one is the unidimensional case. We have only one input x, one output. Then we're going to have the same number of input and output, but these are going to be greater than 1. And finally, we're going to have one output, but several inputs. In the first case, we're going to look specifically at linear systems. Okay, so system where my output equals ax plus b, where a and b are simply constant and x is my random variable. I'll know the PDF for x. I'm going to seeking for what is the PDF for my output y. So let's look at a simple case here. One input, one output. So y equals g of x. So I have my input PDF here for x. I have my function y equal ax plus b. And I have my output, my PDF for y. I know this PDF. I'm looking for this PDF at the output. And I can represent this relationship between I must satisfy this equality. So f of x times dx, the probability content defined on a neighborhood dx, must be equal to the probability content defined on my probability domain dy. So if I want to satisfy this, I can say I'm going to send that dy on the right-hand side of my equation. So I can say that my PDF for y is going to be my PDF for x times the absolute value of dx divided by dy. Why absolute value? Because we must maintain that no matter what is the sign of this term, I need to have my f of y that is greater than 0. So for the generic case where y equals ax plus b, where a and b are constant, I can define my dy dx in absolute terms. I have simply the absolute value of my coefficient a here. So we can see that for x, if I know mu x and sigma x, the mean and standard deviation, For y, my output mean is simply going to be a mu x plus b. My output standard deviation is going to be the absolute value of a times the standard deviation of my input x. So we're going to look more closely at where does this come from. So let's assume that my input x as this Gaussian PDF or normal PDF with mean 10, standard deviation 5, so variance 5 squared. And my function is going to be y equals 2x. So I can represent my PDF or my Gaussian random variable, my normal variable, like this, what we saw earlier. My dx, so if I differentiate this with respect to x, I'm simply going to obtain 2. So using the change of variable rules we just saw the previous slide, we can obtain what's going to be my PDF for y by multiplying my analytical expression for the PDF of x times the absolute value of dx dy, where dx dy is simply the inverse of what I have obtained here. So what I'm going to get, I'm going to evaluate my PDF for x at my relationship x equal y over 2 times the inverse of this, 1f. So if I replace these values in the expression of my PDF, I'm going to get this. And if I reorganize these terms, I'm going to get this, which simplified to this is equivalent to my Gaussian random variable, where I double the mean and I double the standard deviation. So this is the same rules we saw on the previous slide. So for instance, we can see here visually, if this is my mean 10, standard deviation 5, if I project these on my linear function y equal to x, I'm going to get that linear projection for my output PDF y. This was for the univariate case. Let's look at the multivariate case. So in this case, we have two dimension. So we have our domain x, we have our domain y. I want to apply the same thing. I need to say that these rules apply. So meaning that the probability constant in the neighborhood dx must be equal to the probability constants in the neighborhood dy. So in that case, I use the same technique. I'm going to send my dy on the other side. And here I'm going to define j, which stands for the Jacobian, which is going to contain the partial derivative of my output y with respect to my input x. And that Jacobian of y given x measure the size of the neighborhood of y with respect to x. So my full Jacobian matrix is going to be in the case here where n equal n by n matrix, containing all the partial derivative of my y with respect to x. And this Jacobian, each line represents a gradient vector. So the first or the ith output with respect to all of the jth input. And my dx dy that I have here, in this case, represents the inverse of the determinant of the Jacobian matrix here. So again, as we saw earlier, the determinant measures how much the Jacobian will expand or contract the space around my neighborhood. So my dy dx is going to be simply the determinant of my Jacobian. So I can obtain in a generic way with my change of variable rule the PDF for f of y, knowing the PDF for f of x as the inverse of the determinant of my Jacobian. So that might seem complex, but we're going to see for Gaussian or normal random variable, this gets very simple and really efficient. So in this case, if I have a linear system, so y equals ax plus b, where x is random, a and b are going to be either a deterministic matrix or a deterministic vector. So x is my Gaussian random vector, defined by its mean vector and its covariance matrix. So we can have these following size. So if I have x, which is n by 1, A is my deterministic matrix n by n. A is directly, in the case of a linear system, going to be my Jacobian, okay? And my output, since this is n by n, is going to also be n by 1. And B, my deterministic vector, is going to be n by 1. So in that case, I can define the output statistical moment of my Gaussian random variable y as having a mean amx plus b, which is the equivalent of evaluating my input mean in my linear system. And my output covariance is going to be a sigma x a transpose, where in this case of a linear system, the a is equivalent to my Jacobian. Okay, so very easy to propagate exactly Gaussian random variable into linear system. And we know for a fact that the output is always going to be Gaussian as well. So it's fast and it's efficient, and we're going to rely on this in the context of probability theory. Finally, third case where we have one input and one output and more than one input. So a function y, which is unidimensional, equals ax plus b. So in this case, going to be the same thing, the same mean vector and covariance. Basically, define my random vector x. I'm going to have y, which is a 1 by 1 output value. I'm going to have a gradient vector, which represents my gradient a. X is going to be n by 1 dimensional vector, and b, which is going to be a scalar term. So in that case, my mean output is going to be amx plus b. My output variance is going to be gradient times sigma x times gradient transpose. Okay, so we saw the case here of linear system, y equal ax plus b. What do we do if we don't have this form and g of x is nonlinear? And this is actually what we're going to have with reliability theory. What we do, simply we linearize. Okay, so we're going to say that we're going to apply say first or second order Taylor series expansion on that linear function. So we're going to linearize the system at the expected value for x. So basically, if we look at this, we're going to look at the general definition. How can we approximate this by a Taylor series expansion? We're going to look at the first order Taylor series expansion, and then we're going to see how this expansion can also give us knowledge about the relative importance of the variables. So first, imagine that we have as input variable x, defined at mean 10, standard deviation 5, and we have that nonlinear function y equal g of x. So what we're going to do for such a nonlinear system, if we want to propagate uncertainty through it, is that we're going to locally linearize that function at the expected value. Why at the expected value? Because this is where we're going to add the highest probability content. So we want to minimize the error where the probability density is the highest. So at this point in my function, I'm going to take the derivative at the expected value. And then I'm going to simply use the same equations we saw earlier to propagate the uncertainty through that linear system that is approximated. So basically, to have that first order Taylor series, that local linearization, is equivalent to say that my nonlinear system y equal g of x is going to be approximated by y approximately equal to g of mx plus the gradient evaluated at the mean value times x minus its mean, where g of mx is the gradient. So keep in mind that for a nonlinear function, where you evaluate that gradient matter. And in our case here, we're always going to evaluate the gradient at the expected value for our input random variable. So this would be a first order Taylor series expansion, but we could go further and have, say, a second order Taylor series expansion. Okay, and this is what is going to differentiate what we're going to see in the first part of the course, I think in module 6 as form versus what we're going to see later on, I think in module 12 as SORM, second order reliability methods. And we can generalize this for nth orders. So for the first order realization, this is basically a first order linearization of our nonlinear function at the expected value. So it's basically boiled down to this equation. So we're going to represent our nonlinear relationship by the function evaluated at the expected value times the gradient evaluated at the expected value times x minus mx, meaning that my output expected value is going to be my function evaluated at the input mean. My output variance is going to be approximated by the gradient evaluated at the mean times covariance times gradient transpose. And finally, last thing we want to see is that whenever we have these coefficient A in our linearization, we can use this by multiplying them in absolute values times the standard deviation of the input to measure the importance of that ith input variable into the output variable. And we're going to use this later on, I think in module 10, when we're going to look at sensitivity analysis. How much each variable is important in calculating my probability of failure for my structure of my system. And at the end, we can see that this relative importance of each variable is both function of how much my function transform my variable, as well as what is the uncertainty associated with my variable as quantified by the standard deviation. So if we summarize what we've seen in this revision module about probability theory, we saw that probability represents not something that is inherently random or arbitrary unpredictable. It represents our knowledge about some quantities. And the less we know about the quantities we deal with, the more we should use probability theory. So we're going to rely here on that Bayesian interpretation where the probability of an event EI measures the relative plausibility of its occurrence with respect to all possible events. It's not something that is fixed in time. That inherently represents our knowledge of what this value could be. And this is what we characterize as epistemic uncertainty. So uncertainty related to our knowledge of some quantities. So we saw some operations. So the intersection, union is a subset of, belongs to. We saw the fundamental axiom, probability must always be between 0 and 1. Probability of the sampling space is 1. If two events are mutually exclusive, we can represent the probability over the union as simply the probability of the two events. We saw in the general form the inclusion-exclusion rule where we want to do the probability of the union of events. So we first sum the probability of the events taken separately, then minus the probability for pairs of events, plus probability of triplets, etc. And we're going to asymptotically converge to the correct value. We saw how can we define Bayes' theorem true conditional probabilities. We saw probability density, probability mass function, cumulative density function. We saw that what are the key parameters for the normal, univariate, and multivariate PDF, so the mean, standard deviation, and correlation coefficient. We saw how to define multivariate probability density function or probability mass function, whereas that joint PDF is always greater or equal to 0, and again, the integral or the sum must make 1. We'll look at conditional probability, how we can learn from observation. So given that I observe x2, how does it modify my knowledge of, say, x1? And in the case where x1 and x2 are statistically independent, observing x2 don't change my knowledge of x1. In a general case where x1 is not independent from x2, we need to use the chain rule of derivation to express that joint PDF between my n events. So we saw the notion of expected value invariance. So we saw that expected value is the weighted sum of the possible realization times their joint PDF of, or the PDF of occurrence. In the case of a continuous random variable, we saw the notion of variance, which is akin to the inertia of a cross section, representing how much my probability density is spread around my expected value. We saw the matrix notation for the covariance matrix, which is going to be a diagonal standard deviation matrix times correlation coefficient times standard deviation matrix. So for random variable, function of random variable, y equals g of x, we see that we can use what we define here as the change of variable rules to say, knowing the input PDF f of x, how can I obtain the output PDF f of y? So we saw that for the Gaussian case, we have exact solution to these things by applying these two formulas, where in our equation for a linear system A mx plus b, it's simply going to be, for the linear system ax plus b, my output mean is going to be a mx plus b, my output variance is going to be a sigma x a transpose. And in the case where g of x is nonlinear, in the context of reliability, what we're going to do is a first order Taylor series expansion, meaning that we're going to linearize our nonlinear equation at the expected value to minimize the approximation error we do. And then we can use these coefficient AI that we use in our linear system, multiply by the input standard deviation to measure the relative importance of the different random variables. So that concludes here what I wanted to do with revision. The next module we're going to see is going to be in detail coverage of all the probability density function we're going to need for the context of reliability theory.